Hello, everyone. My name is Masabali. I will be teaching you the loss function. So, our title is Understanding Loss Functions, which actually drives the model success. So, we will go through an intro about the loss definition, why is it very important, the type of losses, and um, different things separately. So, first of all, think of training a model like as if you're driving a car toward a destination, but how does the car know where to go? How does it correct its path when it veers off? So, actually, you should think about it, about the loss function as the steer, which guides your car. So the loss function tells the model how far it is from the truth. It quantifies the wrongness of a prediction, then helps the model steer back on course. So without the loss function, the model is like a car without a steering wheel. So you have no idea how to reach a specific destination. The definition is, so the loss is a metric which that measures the performance of a model and it quantifies the error between the predicted and the actual target. So, error between the predicted output of a specific model and its corresponding ground truth. Why is it very important? So, first of all, how does it improve the model? So, actually, it tells us how much the model's predictions differ from the actual answers, and this helps improve the model during training by updating the model's weights. So, why do we need it? We need it because we need to evaluate the model's performance and we need to guide the learning process to improve the prediction. What are the specific type of losses? So we have two types. The first one is like the basic one, and the other one is the zero shot. So the basic is like usually very widely used in deep learning tasks. And the zero shot, actually, it is designed specifically for tasks where the model must generalize to unseen classes. And we will talk about each one of them separately and about their um, different losses. So the first loss is the distance-based loss for regression. So as you can see here, this is the network output and this is the target. So in the regression model, you want your network's prediction to be as close to the target value as possible. So we need to minimize the distance between the prediction and the target. So the standard measure, which usually used for the distance between 2 points, is the square Euclidean distance between the two. So the average Euclidean distance between the points in your batch of a training data is actually the mean squared error. So here, let me give you an example. So imagine you need to create a real estate model that predicts the price of houses based on features like size, location, number of rooms. So you can use your loss could be the mean squared error. This is the formula. So as you can see here, 1 over n, n is the number of data points, y hat I is the predicted value, the y minus the yi, which is the ground truth. And from this figure also you can see that this is the true price and this is the predicted price. So the square difference between them is the following error. And also, let me show you the script for this. So first of all, I need to go through this. So this is a template for calling the loss. So actually, whenever you need to call a loss, regardless what kind of loss is that, you need to um, do the following. This is the actually we can say that this is a template. So first of all, there's a training loop. Here you set the model to the train state, and then here you loop through your data set, and here you pass the batch through the forward pass, and then here you have the optimizer, and then here the loss um, you're passing the predictions from the model and the target, and then here's the backward pass and optimization. So for the mean squared error, so here like for example, we can replace it with any loss we want. We can initialize any kind of loss we need. So for example, here, using torch library, the PyTorch, there's you can just say torch.nn. You can initialize it through, like you say, nn.mse loss, and then you pass the predictions and the ground truth. These are dummy values. So let's say that these are like real prices for houses. These are the predicted ones. And then we compute the mean squared error. And by the way, there's something very important. The lower the value of a mean squared error, the better the model. So whenever the value is closer to zero, then your model is better. Okay, so the second type of losses is the classification losses. So for example, if you have a classification problem, the network must output the probability for the class of the training data. So, for example, the network output is like PYI for each of the classes I. So typically computed using what a softmax function. So the ideal output, let's say PYI, must be high. So like ideally it should be 1 for the target class, and PYI for the rest of the classes should be low. So this is captured by the cross entropy loss, where we will talk about shortly. Um, so you should know that this is 0. This when the network outputs up perfect 1 for the target class and greater than 0 otherwise. So let me explain the formula here. So for example, for classifying an image, imagine you need a model that predicts the category of images, let's say cat, dog, or bird. So this is the formula. Um, like 1 over n is the number of data points, and then the c is the number of classes. The yi comma c is the target probability for class C, and the log yi hat comma c is the predicted probability for class C. So for example, what's the objective of this? The objective is to minimize the loss, ensuring that the predictions are closer to actual values. So also this is another plot. Let's say like the true class is cat, then you should have it like with the, let's say, high probability. And this is the cross entropy script. So here also these are the true labels, the class indices for cat, dog, and bird. And these are like logits for these three classes. The probabilities, for example, 1, 2, and 3. And then here you pass them, and then you just print the loss. So also we use the same library. The torch library to initialize the cross entropy loss. Let's continue. So the second, the second type of losses from the classification losses is the binary cross entropy. So for example, in some problems, the network only identify a single class. So for example, if you have a leaf and you need to know whether this leaf is infected by fungus or not. So you provide an image and just you want to know whether this is infected by fungus or not. So actually, you need to identify a single class. So in this case, the network only outputs py for the target class. So it must be 1 for positive training instances, so a picture of a real leaf with fungus, and it must be 0 for negative training instances, which is like a picture of a healthy leaf. So here, although there's only one output, but there are implicitly two output actually, which is like the probability of class py positive, which should be equal to the py, and probability of not the class, which is py negative, which is 1 minus the py. So the binary cross entropy is actually just the standard cross entropy for single class classifiers, where the CE is computed over both outputs, py pos and py neg. And this is also an example, let's say a spam in email detection. So you need to create a model that predicts whether this email is a spam or not. So also, again, the objective is to minimize the loss. So you're encouraging the model to output probabilities close to the true labels. So here's the formula. 1 over n is the number of data points. Yi is the target probability. And the yi hat is the predicted probability. And for example, check this sample. Let's say for this email one, it was identified as true spam. And then this one, let's say not spam, spam, etc. For the BCE, also you just here also we initialize the dummy vector, which is like a spam, which stands for 1, not spam 0, and then the last one 1, which is spam. The predicted probabilities, this is something we initialized also, but usually it comes from the model. And then let's say 0.85, 0.1, 0.95, etc. So, and then we need to compute the binary cross entropy. And then let's say this is how we initialize it. We say nn dot BCE loss, and then again, we just pass the y prediction, y pred and the y true, and then we print it. So these are the classification losses, and we talked about the regression losses. Now, so both of them, the regression and the classification, are basic losses, and they're very popular and used all over the deep learning problems. So for the zero-shot loss, so in the classification losses seen so far, we have tried to train a network to predict specific loss in the training data. The objective was to maximize the classification accuracy of the specific classes seen. And in other zero-shot problems, so our intention is not actually to feed or teach the network about specific classes, but rather you need to derive representations where instances of a class cluster together. Some instances of a specific class, they cluster together and they stay far away from instances of other classes. So the specific classes we provide during training are now just examples of classes. So actually, the network must learn to learn the generic concept of clustering instances from a class together from these example classes. So zero-shot losses promote such learning. So what are the zero shot versus the conventional classification? So in the conventional classification problems, the network actually merely learns to model the classification boundary between two classes in the feature space. So as long as the classes are perfectly separated, then it's happy. You can see that, just there's a classification boundary. And then, for example, but in the zero shot problem, you try to minimize the distance between data points of the same class while maximizing the distance between data points of different classes. So actually, one thing I need to mention about the cross entropy loss, the cross entropy loss is actually a zero shot loss, and the network learns to extract features that are separable from each other by linear boundaries. So in doing this, it learns to generate features where features from the same class cluster together, but only provided there are a sufficiently large number of example classes. So this condition is satisfied if we have large number of classes. So we have already seen the cross entropy loss. So and now the first loss from the zero shot family is the center loss. So in the center loss, we explicitly try to shrink the classes by moving the feature vector for each data instance towards the center of its class. So the loss itself is the total square distance of all these data points from the center of their respective class. So the center is also learned. So it's also a learnable parameter. So this loss is also used along with the cross entropy loss. So we can't use the center loss alone because it's really too small. So for example, let me give you an example. Let's say face recognition system. So the central loss is used in conjunction with other losses, like as we said, cross entropy to enhance the face recognition systems. And the model learns embeddings for face images, ensuring that all these embeddings belonging to the same person are grouped closer to their center in the embedding space. So the objective is what? To minimize the distance between the feature vectors of samples from the same class and their class center. So here's the formula. M is the total number of samples in the batch, and xi is the feature vector for ith sample. Cyi is the center of for class yi. So let's check the code for this. So first we initialize the number of classes, the number of features. As I said earlier, that the centers should be learnable parameters. So we initialize it and we just like here I just added uh, uh, um, the number of classes, comma the number of features, and then we started with a random initialization for the learnable parameter. And then here the forward, here we get the class center for the input labels, and then we compute the squared distance between the features and the centers. And then these distances are clamped to ensure that they stay within a reasonable range, and the mean distance is computed to get the final loss. So also, again, these are embedding vectors, dummy embedding vectors. These are their corresponding classes. We initialized it by passing the number of classes, number of features, and then we just called the center loss past the embeddings with their corresponding labels. After the center loss, we have angular losses. Angular losses, so they distribute the feature vectors on the surface of the sphere by normalizing their length. So subsequently, they work by just minimizing the angle between each data point and the center for its class. So this allows us to introduce a margin, which is the margin is like an additional penalty for being away from the center. So we have the from the angular losses, we have the angular softmax. So let's say you have a face recognition system that checks the people's identities by comparing their faces to photos in the database. So the system needs to make sure that face representations, which are the embeddings, for different people are very different, while face representations for the same person are very similar. The objective is you need to maximize the cosine similarity for the true class, but while you enforce a margin between classes in the angular space. So this is the formula. So here you have the S, which is like scaling factor to stabilize the gradients. This is the cosine similarity with an angular margin M, and then this is the theta, which is angle between the embedding and the correct class center. And the formula for this is the following. So again, we initialize the weights. We initialize the margin, the scale, the features, and then we need the cross entropy loss. Then here we normalize the input and the weights, and then we compute the cosine similarity. And then we subtract the angular margin from the cosine similarity for the true class. And then we scale by the factor that we initialize. So for example, here, let's say we're talking about 2D embeddings. And then these are their corresponding class labels. And then here I initialize and pass them at the same time, and then you get a specific type of loss. So this loss, the angular losses are really good for let's say speaker verification, for face verification, and all of these tasks. So, and then the second type is the additive angular margin softmax, which helps make the classes more distinct in a classification problem because it does this by adding an angular margin between classes in the decision boundary. So it introduces actually angular margin to make it harder for the model to classify samples. So as you can see here, for example, this is the original softmax. You have a decision boundary, but if here you add um, a fixed decision margin. So by adding this margin, you make sure that the decision boundary is becoming stricter. So if they are from the same class, they are pulled closer together. If they're from different classes, they are pushed farther apart. So this improves the model's ability to separate the classes, especially in specific challenging classes. So at the angular softmax, as described by Liu et al., can only impose an unfixed angular margin, whereas the additive margin softmax incorporates a fixed hard angular margin. So this is the exact difference between the angular margin and the additive angular margin. So for example, again, we can, let's say, we can think about speaker verification here. So the system needs to determine if two speakers belong to the same person, and the embeddings of different speakers should be well separated, while embeddings of the same speaker should remain compact. So you need to, the objective is also that you need to maximize the cosine similarity for the true class while enforcing an additive margin to separate the classes in the embedding space. So here, from this formula, you can see here, this is the additive margin where we are subtracting it from the cosine similarity for the true class. And let's check the code. Here's the code. Here you can see it's very similar to the previous one, but here we subtract the angular margin from the cosine similarity. And then again, we just created a random 2D embeddings, class labels, and yeah, that's it. Now we have contrastive losses. So the losses we have seen so far, they all have focused on the relationship of the data instances to their classes. But as a result, the loss for each data instance can be individually calculated. So the contrastive losses are computed by comparing data points to each other's. So look, the red dashed arrow shows that the distance between 2 points of the same class, and the black arrow shows the distance between 2 points from different classes. So the length of red dotted line must ideally always be less than that of the black dotted line. So the contrastive, so they're really computed by just comparing data points to each other's. And they're built on the principle that a data point must always be closer to another data point from its own class than it is to a data point from any other class. And triplet is the most common contrastive loss. So, for example, let's say for a face recognition system, a system needs to determine if these two face images belong to the same person. So it unlocks a phone with your face. So, for example, the anchor is the your stored face image. The positive is the current image of your face, and the negative is the face image of someone else. So also so this is the margin, and the objective is that you need to minimize the distance between the anchor and the positive embeddings while ensuring that they are farther from the embedding by a margin what? By a margin alpha. So this is the formula. This is the anchor. This is the positive sample. And this is the negative, which is a different class from anchor. And then this is the margin, which ensures that the negative is sufficiently farther um, than the positive. And here is the triplet loss. So so this is, I initialized the anchor, then the same class as the anchor, and then the different class from anchor. And then we compute distances using pairwise distance. between anchor and positive, anchor and negative, and then you compute the triplet loss, which is like you apply the ReLU to ensure that the loss is non-negative, and then you just say positive distance minus the negative distance plus the margin. And these are references and further readings. Thank you for listening.